Alrighty, welcome to Chapter 9. This chapter is going to be a little bit trickier and different than the previous chapters because I'm going to use a combination of new videos mixed with older videos that are about the same topics but based on a slightly different book. And so, just go along and try to make the most sense of it as you can, and feel free to ask lots of questions in class. So we'll get started with Section 9.1, Graphing Quadratics. So first, the important vocabulary words. With quadratic equations, this is something we haven't spent much time with in previous classes. So sometimes the material we're covering is mostly a review, but in other cases it's going to be almost all new. And so this is a case where everything is new, so we're going to have a lot more vocabulary than normal. First thing is quadratic function. A quadratic function is any nonlinear polynomial of degree 2. So you already learned nonlinear means when you graph it, it won't be a straight line, it'll be curved. Polynomial is a sum of terms, each of which can have variables, coefficients, and only positive exponents. So the degree of a polynomial is the highest power of the exponent. So degree 2 means the highest power in your quadratic function is going to be an x squared. Okay, so the parent function, which is the basic function, this is like the easiest possible. So a parent function is essentially the easiest possible one, and then all the other ones are going to be more complicated and built off of this easy basic one. A quadratic easiest parent function is just x squared, all by itself with nothing else. So y equals x squared or f of x equals x squared. And all other functions for quadratics can be thought of as complications or expansions upon this basic function. So the standard form, what's the most complicated it can get? Well, we can have a coefficient in the front, a, x squared. We can add another term, bx, and we can add another term, c. Now this c, let me cross it off right here. I'll put it right here. Sorry for that formatting. Okay, so we can have a quadratic part. This part is called the linear part because it's x to the first power, and this part is of course constant. So ax squared plus bx plus c. This is the standard form of a parabola. You need to memorize this as soon as possible. Okay, the functions themselves are called quadratics, but once you graph it, it's called a parabola. So a parabola is the name of the graph itself. So once you graph all these quadratic functions, they're going to look kind of curvy and like this, going up on either side. Or if they're upside down, they might look like this. Okay, so this shape is called a parabola, but the equation or function which leads to it is called a quadratic equation. Okay, keep going. 5 more vocabulary words. Sorry about all this. The next one is called the axis of symmetry. So an axis of symmetry is a vertical line that breaks a parabola in half. As I just showed, a parabola looks something like this, and the left side and the right side are the same. So the axis of symmetry is a vertical line. Excuse me. So the axis of symmetry is the vertical line that goes right down the middle, and it goes through this point at the bottom of the parabola if the parabola is right side up, and this point right here is called the vertex. So on the next slide I'm going to show a big picture that has all this stuff labeled. So right now just write down these vocab words and then we'll draw the picture and label them in a second. The vertex is the center point that the axis of symmetry goes through. So again, if the parabola is upside down, the vertex would be, I'll just draw a quick one, there's parabola, vertex would be right there, the center point. The minimum is the lowest point on a graph. That's a pretty obvious regular English word. The maximum is the highest point on a graph. So for parabolas with respect to maxes and minimums, both the max and the minimum will always occur at the vertex. If it's a graph that's right side up, it's the minimum at the vertex, and if it's upside down, it's a maximum at the vertex. This is the highest it goes. And lastly, the roots. We've had roots before with linear equations. Another name for a root is an x-intercept, and there could be 2, 1, or 0 depending on how the graph looks. So we'll take a look now at the graph showing all this kind of stuff. Okay, sorry for a little bit blurry, I copy and pasted it. So the line of symmetry is the vertical line down the middle of the parabola separating the left half and the right half, and it goes through the vertex. The vertex is the lowest or highest point that's dead center symmetrically left and right. The y-intercept is of course wherever you cross the y-axis, and the x-intercepts, in this case there's 2. So notice because the graph goes down and then comes back up, there are two places where it crosses the x-axis, and we'll see how those are related to the factoring that you've been doing in the previous chapter. But also, you could have a parabola that's up here somewhere, in which case it doesn't have any roots because the line never crosses the x-axis, and this would be an example of a graph that's not factorable because you can't find any roots for it, because there aren't any roots. And lastly, you could have a graph that's just perfectly right on the axis, in which case there would be only one root instead of two roots. So we'll learn about all three cases. We're going to spend a lot of time kind of diving in and out of the different factors, vertex form, quadratics. It's a big topic, and there's lots of ways to approach it, and there's no right or wrong way to start, and there's no right or wrong way to go through it. And so we're going to kind of come at it from different angles, and hopefully by the end everything will be all synthesized together. Alright, problem solving tips. The a value, remember the equation was y equals ax squared plus bx plus c. That's the standard form. If a is positive, that's the very leading coefficient, the parabola opens upward, so you'll have a parabola opening upward like this, and therefore the vertex will be the minimum or lowest point. If the a value is negative, if the leading coefficient is negative, that means the parabola opens downward. It's upside down, and therefore the vertex must be a maximum. We're going to spend some time looking at stretching and shrinking parabolas as well as reflecting parabolas, upside down and right side up, in another section, but that all ties back to this a value. This a value tells you whether it's upside down or right side up. If it's positive, it's right side up. If it's negative, it's upside down. Okay, the line of symmetry, that's the line, the vertical line right down the middle of the parabola, and therefore also the x-coordinate of the vertex, because they're aligned with each other. There's a way to calculate that if you have the equation in standard form and you know the a value and the b value. This is a very, very, very important and useful equation. So the x-coordinate of the vertex or the line of symmetry, because they both go through the same point, is negative b over 2a. So if you know b and you know a, you can easily get the x-coordinate of the vertex. We're not going to prove this right now, we're just going to accept it and use it, but in a later section we'll actually prove why this makes sense, and it's not just some random, occurrence. So definitely you want to memorize the standard form equation of a parabola, and you want to memorize the vertex shortcut to get the x-coordinate of the vertex. Once you know the x-coordinate of the vertex, or the line of symmetry, right here, if you want to find the y-coordinate, just like always, you plug the x value in to the equation and you get the y. So once you know x, say x equals 3, plug in a 3 and you'll get out the y-coordinate, and then you can get the x comma y as an actual coordinate point, and that will help you a lot when you're graphing the parabola, because you can now plot the vertex, which is the key point for starting all parabola graphs. Okay, some more problem solving tips. I know this is a long section. You can find the y-intercept by setting x equal to 0. Well, of course you knew this. This is how it's always been, whether it's a linear equation or a quadratic or any other kind of equation. So if you have y equals ax squared plus bx plus c, standard form, if you set x equals 0, this term is gone, this term is gone, the only thing left is the c value. So in standard form, c is the y-intercept. If you have the parabola in any other form, then you can just set x equal to 0 and solve for y, and whatever you get must be the y-intercept. Okay, another important thing to do, or a shortcut that will help you immensely, is to memorize the graph of the parent function, y equals x squared. So I'm going to go over that real quick. If you make a t-table for x and y, for this function y equals x squared, if you plug in negative 2 squared is 4. If you plug in negative 1 squared is 1. If you plug in 0 squared is 0. If you plug in 1 squared is 1. And if you plug in 2 squared is 4. And you notice that the negative side is symmetrical to the positive side. That will happen for all parabolas. They're always symmetrical for the line of symmetry, and in this case the line of symmetry is the axis. So I've got a point here, 0, 0. I've got a point here, 1, 1. I've got a point here, negative 1, up 1. And I've got a point over 2, up 4. And over 2, up 4. So my parabola kind of curves up like this. And now the key to graphing these, you don't need to make a table every time because this is a square. So the outcome is always a square number, and your perfect square numbers we memorized in chapter 8. They are 1, 4, 9, 16, 25, etc. So the first one, you go over 1, up 1. That's a perfect square of 1. Then you go over 2, from the vertex, over 2, up 4, because that's a perfect square of 2. Then you would go over 3, up how far? All the way up to 9. So this is up 1, this is up 4, this is up 9, all measured from the vertex. Okay. So let me skip down here. I said if a equals 1. So note this basic parabola, the coefficient is a 1. So if a equals 1, all the y values are perfect squares relative to the vertex. So relative to the vertex, up 1, up 4, up 9, up 16, etc. But you could also think of these points relative to each other. So the first one, I went up plus 1, from 0 to 1. Then the next one I went from 1 to 4, which from here to here is plus 3. Then I went from 4 to 9. Well, that's plus 5. Then I would go from 9 up to 16. Well, that's plus 7. So if you're jumping from point to point, you have what's called a successive difference, which means each time you go up by 2 additional compared to the one before it. If you compare those points to the vertex, then they're all perfect square numbers. So personally, I typically do my perfect squares, all perfect squares relative to the vertex, but you could also do the points jumping from one point to the next and do an increase in the jump size by 2 each time. Okay, so this is the parent function. It's always starting at the origin 0, 0, y equals x squared, basic graph, and you go left and right, same amount, perfect squares up. Okay, so graphing this one is pretty straightforward. But what happens when it gets shifted left or right and the vertex is somewhere else, or it gets reflected, or it gets stretched or shrunk? So graphing all those variations can be kind of tricky, and we'll spend a lot of time looking at all the different things you can do to a parabola. But this is also a very, last resort backup reminder. If you're totally stuck, it doesn't matter how nasty or complicated a graph is. If you're totally stuck, you can always graph using a t-table. Okay? So find the vertex using your shortcut. Remember, your shortcut is x equals negative b over 2a. Find the vertex, and then make a t-table of some values to the left and some values to the right, and just plot points, and you'll always be able to get it that way. Alright, that's it for the new notes, and we're going to now do the examples, which, yes, you do have to copy down, but since this is a long video, if you want to take a break, now's a good time to do it. Okay, so welcome back from your break if you took one. We're going to now do a couple of examples so we can make sense of all that stuff. It says use a table of values to graph each function. So let's try this first one. Table of values. So we want to make our x, y. Let's try negative 2, negative 1, 0, 1, and 2. Okay, if I plug in negative 2 squared is 4. 4 minus 4 is 0. Plug in negative 1. Negative 1 squared is positive 1. Subtract 4 from that, and I get negative 3. Plug in a 0. 0 squared is 0. Minus 4 is negative 4. Plug in a 1. 1 squared is 1. 1 minus 4 is negative 3. Plug in a 2. 2 squared is 4. 4 minus 4 is 0. So again, you notice they're symmetrical around this point. So this point must be the vertex. So 0, negative 4, puts my dot right here. Then I can plot these other points. Negative 2, 0, that's going to be right here. Negative 1, negative 3, that's going to be right here. Over 1, down 3 is going to be right here. And over 2, there. So I can draw in my parabola by kind of curving this way. Not easy to draw with a mouse. Okay, but now, I don't want to just say, okay, we're done and move on. I want you to look at it and see if there would have been an easier way to graph this. If I knew my vertex was right here, suppose that you had a way to know the vertex was right here, then how could I get the next point? Instead of having to make a t-table and plug stuff in, from the vertex, because the coefficient is just a 1, it's a normal graph, I could go over 1, up 1. Okay, over 1, up 1, because 1 squared is 1. Then I could go from the vertex over 2, up 4, because 2 squared is 4. And I know it's symmetrical, so I could go backwards 1, up 1, backwards 2, up 4. How about the next point? Without doing any t-table at all, I can go over 3, up 9, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, and I know my next point has to be right here. So if you can find the vertex first, then plotting the parabola becomes a matter of following this pattern rather than making a big t-table. So I highly, highly recommend you get this pattern down in your head: over 1, up 1, over 2, up 4, over 3, up 9, etc. That will help you immensely. Okay, let's take a look at the second one. We won't do the whole thing, but let's look at these bits and pieces. Here there's a negative sign in the front, which means we know the parabola is going to be upside down. Okay, and the y-intercept, or starting value here for this parabola, is just +3, and there's nothing else tricky about it. Our parent function is a normal graph. It's flipped upside down, and it starts up 3. So I'm going to do it shortcut-wise. We go up 3. That's my vertex. Now instead of going over and up, because the negative sign, I'm going to go over 1, down 1, over 2, down 1, 2, 3, 4, over 3, down, there's 4, 5, 6, 7, 8, 9. And then symmetrical left and right, so backward 1, down 1, backward 2, down 4, backward 3, down 9. And without even making a t-table, which is the recommended way to do it, I can do this right here. Okay. It also says state the domain and range. Well, the domain is all the possible x values. I can go left and right forever, so the domain would be all real numbers. But the range is the y values. So if my parabola is opening upward, the range would be everything, including the vertex and vertically above it. But for the parabola opening downward, the range would be the vertex and everything vertically below it. Alright, next set of examples says find the vertex, the equation of the axis of symmetry, and the y-intercept. Okay, we don't have to graph these, luckily. So to find the vertex, we remember, let's do number 4. We remember that the x-coordinate of the vertex is negative b over 2a. That's our formula. So we need to be able to identify a, b, and c. So a is 2, b is negative 8, and c is positive 6. So negative b, well, b itself was negative 8, so negative of a negative is positive 8. Divided by 2a, well, a is 2, so 2a is going to be 4, and 8 divided by 4 is 2. The y-coordinate of the vertex, we're going to take this x-coordinate and plug it into the equation to get y. So we have 2 multiplied by 2 squared minus 8 times 2. So again, I'm just plugging in the x-coordinate that we found using the shortcut formula into the equation to find the y-coordinate. Plus 6. So follow PEMDAS here. 2 squared is 4. 4 times 2 is 8 minus 8 times 2 is 16 plus 6. And finally, y-coordinate of the vertex. 8 minus 16 is negative 8. Negative 8 plus 6 is negative 2. So our vertex is 2, negative 2. What else did we have to find? It says find the axis of symmetry. So remember, the axis of symmetry is a vertical line. So the equation is x equals 2, because the x-coordinate of the vertex is the same as the x value of the axis of symmetry. So we label that axis. And remember, a vertical line is x equals and then a number. Axis of symmetry. And lastly, the y-intercept. Okay, to find the y-intercept, we have to plug in x as 0. But because this is in standard form, the y-intercept is the c value. So y equals 6, which means the coordinate point 0, 6 is the y-intercept. Okay, so finding the vertex involves using the shortcut, negative b over 2a for the x value, and then plugging that in to find the y value. That's the same x value as the axis of symmetry. So if we were to plot this, I'm not going to do the whole thing, but vertex is at over 2, down 2, okay, which means there's an axis of symmetry vertical line right there, and then the parabola obviously will look something like this, and then it crosses right here on the y-axis as 6. Alright, that's what we found out. That point, and this axis of symmetry, and the exact curvature of the parabola. Now before I had been saying over 1, up 1, but this one has an a value, a equals 2. So that means it's not going to fit that simple pattern. It will be a little bit more complex, and we'll talk about that another time. Alright, last example. Consider whether each equation has a max or a min. State the max or min, and state the domain and range. Alright, let's choose a tricky one. Let's choose number 9. Y equals negative x squared plus 4x minus 1. So you see this minus sign. That means that our parabola is upside down. Okay, if it's upside down, it looks like this. And if it looks like this, that point where the vertex is going to be a maximum. Okay, so this is our max value. So this function has a maximum, and it says determine the value of this function, or this maximum. Okay, the value is the output or y-coordinate. So we actually have to find that value. So we're going to need to find the y-coordinate, but before we find the y-coordinate, we need the x-coordinate so that we can plug it in. So the x-coordinate of the vertex is negative b over 2a. Okay, b is 4, so that's going to be negative 4 over 2a. a is a minus 1 right here. This is a minus 1. So 2a is minus 2. So the x-coordinate of the vertex is 2. So the y-coordinate of the vertex, just like before, we plug in a 2 to this equation. Negative of 2 squared plus 4 times 2 minus 1. This order of operations is important here. It's 2 squared, which is 4, and then the negative sign. So this is negative 4. Important to do the minus sign after you square it. 4 times 2 is plus 8 minus 1. So the y-coordinate of the vertex, negative 4 plus 8 is 4. 4 minus 1 is 3. Okay, so this point right here is 2, 3. That's what we found out. Okay, so the maximum value of this function, the highest that it ever goes, is 3. Okay, so this right here is the max value of the function. Every single y-coordinate over here and every single y-coordinate over here is a lower value. What is the domain and range? Again, domain is all the x values. So the domain is all real numbers. And the range for this problem, again, for problem 9, is y is less than or equal to 3. Can you see why that is? Y-coordinate value is lower than 3 or equal to 3 are okay, but there's nothing higher than 3. So max and mins, domains and ranges, all are related to parabolas. The domain should always be all real numbers though, because you can always go to the left and you can always go to the right. You just have a limit on whether you go up or down, depending whether the parabola opens up or opens down. So I know this was a long video. You've only been assigned one section this time. So come into class with lots of questions. We'll do a little bit more examples. Alright, that's it. See you later.